Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying functions lecture 3 and we'll be talking about log functions and exponential functions in this lecture. We have already studied basics of log functions and properties of log functions in these specific two lectures, right? So we'll be covering inequalities, graphs and certain problems related to domain in case of log in both exponential functions, okay? So let's have a refresher of log functions. Y equals to log base ax where a can be either greater than 1 or a less than 1 greater than 0. So we have these two cases for a and a cannot be 1. If you want to understand the logic behind this, you can just refer to the log lectures over here. Okay. But this is the basic part of log which everyone should be knowing. Now let's analyze these two cases individually. So these are certain properties again which you can refer to the log lectures once again. You can just take a screenshot of if you want to remember these properties. Now let's try to understand the case 1 where a is greater than 1. Let's take the case we have where a equals to 2. Let's say this is our function. Okay. So let's plot certain values. We have x and this is y equals to log base 2x. This is y. Okay. So for x equals to 1 by 4, for 1 by 2, for 1, for 2, 4, 8. So for 1 by 4, we'll be having value as minus 2. For 1 by 2, we'll be having a value as minus 1. For 1, we have 0. For 2, we have 1. For 4, we have 2. And for 8, we have 3. This is quite basic, right? Now let's try to plot these in a graph. So let's say this is 1, 2, 3, 4, 5, 6, 7, and 8. This is half and this is 1 by 4 over here. Okay, so for 1 by 4 we have this is minus 1 minus 2, so we have this value over here. For 1 by 2 we have this value over here. For 1 we have this value over here. For 2 we have this value over here. For 4 we have this value over here. For 8 we have this value over here. Okay, so if we plot the graph it would look something of this sort. Okay, it's actually touching over here, so it would look something of this sort, basically increasing function. Now you can clearly see that as the values of x are increasing, the value of the function is also increasing. As the value of x is increasing, the value of function is increasing. We can say that if x1 is greater than x2, then definitely fx1 is greater than f of x2. Now this is the case where a is greater than 1. The function is increasing, log function is increasing in case a is greater than 1. Now let's take the other case where we have a less than 1 greater than 0. Let's say we have log 1 by 2 base and x. Okay, let's try to plot this once again. We have x over here, we have y over here. So the first, we can take just the replica of this one. So we have 1 by 4, we have 1 by 2, we have 1, we have 2, we have 4, and we have 8. So for 1 by 4, it would be 2. For 1 by 2, this value would be 1. For 1, it would be 0. For 2, it would be minus 1. For 4, it would be minus 2. And for 8, it would be minus 3. Again, if we try to plot this one, now this would look like exact replica of the previous one. So this would look like something of this sort. The other graph looked like this one. It looked like this one, right? When we had a base of 2, it looked like this one. But in this case, it would look like this one. And in this case, we can clearly say that as the value of x is increasing, the value of function is actually decreasing. So what we can conclude over here, if x1 is greater than x2, then f of x1 is less than f of x2 in case where fx is log ax and a is less than 1 greater than 0. So in this case, the function would be a decreasing function. As x is increasing, the function value is decreasing. Okay. Now let us try to understand the logarithmic inequalities for case 1. So case 1 is where a is greater than 1 and let's say a equals to 2. So we are again considering the case of log base 2x and let's say the inequality says it's greater than 5. Now what we can write over here is log base 2x greater than log base 2 32. 5 can be written as log base 2 32, right? Now we saw that in case of a greater than 1, if x1 is greater than x2, then log base a x1 is also greater than log base a x2, and vice versa. This is interconvertible in case of a is greater than 1, right? Now if this is true, then we can definitely write x is greater than 32, right? So this is how we have to solve the inequality. This is a very crude case, not a very typical case over here, but this is how you have to do. Now let's try to understand the exact opposite case, that is a is less than 1 and greater than 0. So let's say a equals to 1 by 2. So the inequality says log 1 by 2 base x greater than 5. In this case, we can write 5 as log of 1 by 2, 1 by 2 raised power 5. Let 1 by 32 basically. Log of 1 by 2 x. Okay. Now we know that in this case where a belongs to 0 to 1, if x1 is greater than x2, then f of or log a x1 is less than log a x2, right? We have to change this inequality sign over here. Okay. Using that, we can clearly say that x is less than 1 by 32. This is how we have to utilize. We have to always check what is our base, and based on that we have to change our inequality signs, right? And this all is happening, and this all is happening because of this decreasing function and increasing function. In this case the function was increasing, in this case the function is decreasing. Okay, now let's solve this question. So we have log base 7 x square minus 4x minus 5 less than equals to 1. So in all such inequalities, we have to first consider the domain restriction. So it would be x square minus 4x minus 5 greater than 0. Why? Because anything inside log should be always positive. Now second restriction would be log base 7 x square minus 4x minus 5 less than equals to log base 7 7. We can write one as log base 7 7, right? Now when we have base greater than 1, in that case what we can do, we can directly use the same inequality sign for the arguments. So we can write the second condition as x square minus 4x minus 5 less than equals to 7. Okay, so now we have to solve these two inequalities and find out the answer. So for the first inequality, we have x square minus 4x minus 5 greater than 0. We can factorize this as x minus 5 and x plus 1. Okay, now this means x belongs to minus infinity to minus 1 union 5 to infinity. Now in this case we have x square minus 4x minus 12 less than equals to 0, right? So that would mean x square minus 6x plus, sorry, x minus 6 x plus 2 less than equals to 0. That would mean x belongs to minus 2 to 6, right? Now we have to take the intersection of these two conditions, right? So when we plot the number line, so we have minus 1 over here, we have minus 2 over here, we have 5 over here, we have 6 over here. So we have got open circle this, we have got minus 2 close circle to minus 6 over here, and we have got open circle here and towards minus infinity. So the common regions are these ones and these ones. So x belongs to minus 2 to minus 1 union 5 to 6. Okay, so a seems to be the correct answer. Now let's solve this. Log of 1 by root 3 log 6 x square plus x plus 4 less than 0. Again we have to apply the domain restriction. Domain restriction says first condition would be x square plus x divided by x plus 4 should be positive, right? That is our first condition. Now this argument itself is inside this log, right? So that means this should always be positive. That would mean log base 6 x square plus x divided by x plus 4 should be greater than 0. Now 0 can be written as log base 6 1, right? And we have base as 6, that is greater than 1. So what we can write over here, x square plus x divided by x plus 4 should always be greater than 1. Now this is our second condition. Now for third condition, we have log 1 by root 3 log of 6 x square plus x divided by x plus 4 less than 0. Now we have base as this one. So if we remove this base, and let's write this as log 1 by root 3 1. When we are removing this base, we are left with log base 6 x square plus x divided by x plus 4 greater than 1, right? Why? Because we had a base which was less than 1 greater than 0. In this case, inequality sign would change. Okay. Now again, if we want to solve this one, we can write this as log base 6 6. If you want to solve this further, we have to again consider base over here, that is greater than 1. So when we are removing this log, we are eventually getting x square plus x divided by x plus 4 greater than 6. So this is our third condition. It became a little haphazard over there. Now if you observe it carefully, if this is greater than 6, then automatically it would mean that this is greater than this one and also this one. So if this is holding true, this would satisfy and also this would satisfy. So basically we have to solve just this one and not all three. Okay, so let's try to solve this one. So we have this to solve, right? Now what a lot of people would do is cross multiplication of x plus 4 with 6 and then solve it, but that shouldn't be done unless we know for sure that x plus 4 is always going to be positive. Why? Because let's say we have an inequality 10 upon minus 5 greater than minus 3. This is minus 2 and this is minus 3. So this inequality is correct. Now let's say I'm cross multiplying minus 5 over there. We'll be getting 10 greater than 15, which is not true, right? This was true, but this is not true. Why did this happen? Because we multiplied minus 5 over there. That was negative. So when we are removing negative sign from this ratio, this fraction, in that case, the sign of this fraction would change. So earlier it was a negative number. Now it has become a positive number because we have removed minus 5 over from here and we have multiplied it over there. So in that case, we have to change the sign. But in case of variable, we don't know if this is positive or negative, right? So what is the best way to do it? We can do x square plus x divided by x plus 4 minus 6 greater than 0, right? Now we can do LCM over here. That would give us x square plus x minus 6x minus 24 divided by x plus 4 greater than 0. So we are getting x square minus 5x minus 24 divided by x plus 4. And if we try to factorize it, we'll be getting x minus 8, sorry, x minus 8 x plus 3 divided by x plus 4 greater than 0. If we use the wavy curve method over here, so the critical points are minus 4, minus 3 and 8. So plus minus plus minus. So the answer would be x belongs to minus 4 to minus 3 union 8 to infinity. So C seems to be the correct answer. Now I'll keep this question as homework because this is more or less similar to the previous question. We have different types of bases over here. This one is of this type and this one is of this type, right? So we have two types of bases. We just have to take care of the inequality sign. Okay. Now let's solve this question. So we have log base x, 6 minus x greater than 2. In this case, we have a variable base over here, right? So we don't know if x is greater than 1 or x belongs to this range. We don't know, right? Now, therefore, we have to take the cases over here. So the case 1 would be x is greater than 1. So equation would become log base x 6 minus x greater than log base x x square. You can write 2 as log base x x square, right? And now we have assumed that x is greater than 1. In that case, we can directly remove these logs without changing the sign of inequality. So 6 minus x greater than x square. So that would eventually give me x square plus x minus 6 less than 0. That means x plus 3 x minus 2 less than 0, right? So x belongs to minus 3 to 2, right? Now if we talk about case 2 over here, so we have x is less than 1 and greater than 0, right? Now if we write the inequality over here, log base x 6 minus x greater than log base x x square. In this case, we have assumed that this is the case where x is less than 1 and greater than 0. So we have to change the inequality sign once we are removing the logs, right? So we have 6 minus x less than x square. That would give me x square plus x minus 6 greater than 0. That means x plus 3 x minus 2 greater than 0. So x belongs to minus infinity to minus 3 union 2 to infinity. Now the interesting thing over here is, in this case we had assumed that x is greater than 1, but we are also getting numbers, some negative numbers over here, right? So what we have to do, we have to take the intersection, because eventually this was the condition based on which we have to find out the values of x, right? So we have to conform to this inequality over here, that is x is greater than 1. So on taking the intersection, we'll be getting x belongs to 1 to 2, right? Now in this case, we had assumed that x belongs to 0 to 1, but we are getting these kind of values, right? So there is nothing in common between this and this. The intersection would be null set. So the final answer would be this only. That is A option. Now let's talk about exponential functions, and we'll get to understand why we are studying exponential functions right after log functions. So in case of log functions, we had x equals to log base a y, right? Now this equation can be written as y equals to a raised per x, right? This we studied back in our log chapter, right? Now this base a and this base a, they both are same, right? So they should have same kind of restrictions. In case of log, we had a should be greater than 0, a should not be equals to 1. We have same kind of restrictions over here. A is positive and a is not equals to 1, right? Now a lot of people think that e raised per x is exponential function. Yes, it's an exponential function, but it's a special case. So we have base as e over here, that's a special case of exponential function, but the actual exponential function is y equals to a raised per x. Okay, now we had two cases for log functions, so we are going to have two cases for exponential functions as well. So the first case would be obviously a is greater than 1, the second case would be a less than 1 and greater than 0, right? So these are two cases for exponential functions as well. Let's look at case 1. Again, we'll be taking, let's say a equals to 2. So we are taking y equals to 2 raised per x. Let's plot the graph once again. So we have x over here and y over here. So for x equals to minus 2, minus 1, 1, 0, 1, 2, 3. So for minus 2, we are getting 1 by 4. For minus 1, we are getting minus 1 by 2. For 0, we are getting 1. For 1, we are getting 2. For 2, we are getting 4. And for 3, we are getting 8. So now if you plot this, you'll be getting this kind of graph. Remember, for log functions, we got a graph something of this sort. So it would be a mirror image along this line, that is y equals to x. We'll talk about this later when we are studying inverse functions. But as of now, you can just remember it that this would be a mirror image of this function. My drawing might not be that great, but these two functions are actually inverse of each other, considering that base is same. In that case, we are taking log 2x. Okay. Now the case 2 would be definitely a is less than 1, greater than 0. So let's say we have 1 by 2. So that is 1 by 2 raised per x, y equals to. Again, if we plot all the values of x and y, we can just directly plot the graph over here. That would look like this one. Okay. So this is the graph of y equals to 1 by 2 raised per x. Now again, you can observe over here is this is an increasing function. With the values of x increasing over here, the values of y is also increasing. In this case, this is a decreasing function. Values of x are increasing, but values of y are decreasing, right? So in this case, if x1 greater than x2, that means f of x1 also greater than f of x2. In this case, if x1 is less than, if greater than x2, f of x1 would be less than f of x2, right? So for case 1 and case 2, this inequalities holds true for both log and exponential functions, right? And now that we have discussed log functions and exponential functions in detail and their inequalities, graphs, cases, everything over here, let's end the lecture over here and we'll start with modulus functions and other functions from the next lecture. So let's meet in the next lecture. Thanks for watching.